Good morning, Professor and everyone. Today, our team with my name is Thanh Nguyen and Junior. We to introduce about our team project. Our team project about the light harvesting selenium quantum dots for enhanced mitochondria electron transport chain activity. Uh, let me to first one. Let me to talk about the uh, uh, background. As you know, mitochondria is one of the most organelle of our body, our cell in our body, because all of cell in our body contains the mitochondria. Mitochondria is as a power of the cell to supply the energy for our body. So it's very important, as you know. I don't want to talk about more about the importance of mitochondria because it's as all of you know is a critical role. In the first one, as you know, in the mitochondria inside our cell, and this is about the structure of mitochondria. Uh, the first one, and I just want to say about the important role. Here we can see here is a complex 1 and complex 5 to make the ATP. So you can see here from here to here with the electron transfer. And the one when the mitochondria has a problem, what is this? As you can see, almost of this is from the mitochondria derived from the dysfunction of the electron transport chain. Yeah, as you can see here, it's derived from complex 1, 2, 3, 4, and 5. So that's an issue I want to focus on. The next one, as I mentioned before, almost of our cell in our body has need to mitochondria to make energy. So when mitochondria has a disease or problem, almost of organ in our body has a problem from the heart, eyes, liver, muscle, and everything in our body. So it's very important. And you can see here in the market of the mitochondria on global increase by the time. They estimate about the markets in the mitochondria in the 2000 in next 10 years around more than 700 million US dollar. So it's it's as a burden of our society, but as a challenges in our field. And I want to say about the how to treat about the mitochondrial disease. I can to divide to two kind of method. The first is the conventional therapy, and the second is the recently or novel therapy. About the conventional therapy, they just focus on the how to treat with the relieve the symptom with as a supplemental therapy as a drug or nutrient supplementation. And the advance of therapy, we can use the gene editing or even the mitochondrial replacement therapy or stem cell and both of the conventional or advanced therapy has both of pros and cons. But I want to combine this pros and cons of two therapy. Now I want to set about the results. Is published in 2023. It's very amazing. They use the nanoparticle clone to put in the inner membrane of the mitochondria. As I mentioned before, make ATP, our mitochondria have to process about the electron transfer. When dysfunction in there, we had to make a bridge to connect to it's a complex, and in this research they can put the nanogron in there as a bridge to make the transfer, and they show can enhance the mitochondria function. It's very good, published, but what is issue? As you know, the grown nanoparticle, the first one is as a metal, so and very expensive. So we can we cannot apply variety in our body. And the next one, in this research, they just use the isolate mitochondria. So it's not mean either real cell or living cell. So this is issue. Now I want to develop this with a solution. I'm curious about how I can use other material to non-toxic, and I will use this in the both in vitro, it means living cell, and in vitro. As I mentioned in here, I want to set about press. Press is a technique to find the signal from the just previous here. I can use this technique to detect the electron transfer result in our complex. Uh, Complex, and you can see the mechanism in the slide. And so I want to find another chemical. So I review a lot of the metal or chemical. So I want to focus on the selenium. Selenium is a essential micronutrient, and we eat every day, and it's proved about a lot of function in our body. So that's why I think about it. About it. And the next one, they also use the selenium nanoparticle to treat some disease with the inflammation. But they almost use this with the nanoparticle. Nanoparticle is the size from the 10 to 100 nanometer. So it's quite big, quite small, but it's bigger than compared with the mitochondria. So I want to focus on the smaller the material. Now I want to set about as a Nobel Prize in 2023 about the quantum dot. Quantum dot is a semiconductor of the nanoparticle. It's very small. The size you can see here from 2 to 10 nanometer. So the first one we can see this small size. So in logical thing, it's easier to inside the mitochondria. And the second one, you can see here, when we utilize with the quantum dot, they can electron transfer. It's very important, and I think maybe quantum dot can have electron transfer in our complex in mitochondria. So we have a hypothesis. Our hypothesis is we can use the selenium quantum dot to cheat to mitochondrial disease. This is our diagram to support the first one. We can use a quantum dot, and we need the TTP to target the mitochondria, and after that we can use lights and to mix the electron transfer, and it can help the mitochondrial function. So to more detail aim, my teammates will present about the next one.
Hi everyone, I'm Juan Lee, who's going to make a presentation from this part. There are three aims to study this topic. The first goal is constructing positively charged selenium quantum dots functionalized with triphenylphosphine. TPP functional TPP functionalized selenium quantum dots will interact with negatively charged mitochondrial membrane. ATP, as the main energy source in the cell, is synthesized in the mitochondria via electron transfer chain by using non-radioactive energy transfer pathway that is called plasma resonance energy transfer. If selenium quantum dots are combined with the inner membrane, it will improve ATP synthesis directly. That's the second aim. Finally, synthesized ATP amount will increase because of improved electron transfer chain activity. As selenium quantum dots attach to the inner membrane of the mitochondria, electron transfer rate will become faster, resulting in an increase in ATP synthesis. If we start to conduct the study, brief methodologies are as follows. Selenium quantum dots should be synthesized. Selenium quantum dots are firstly synthesized by using selenium powder or selenite and applying reduction reaction. Then preparing TPP solution with chloroform or methanol, make a mixture of selenium quantum dots and TPP. Finally, we can get refined selenium quantum dots. And then we need to test how selenium quantum dots work. We can check absorption and luminescence spectrum by using UV-vis spectroscopy and fluorescence spectrophotometer to evaluate conductivity and electrical properties of selenium quantum dots. We also measure current voltage. How well selenium quantum dots are synthesized qualitatively is important, so SEM imaging will be needed. Next, in vitro and in vivo experiments should be conducted. For for in vitro experiments, cellular uptakeability quantification, cell viability using mitotracker for imaging selenium quantum dots in the mitochondria will be checked out to test the biofunction of selenium quantum dots. After that, how selenium quantum dots improve mitochondrial functions will be tested. As is well known, changes in membrane potential, oxygen consumption, glycolysis rate, ATP synthesis should be checked. Not only that, we should also check ROS measurement because ROS is one of the main factors that induces mitochondrial dysfunction. After selenium quantum dots are synthesized, we will treat them to mice by oral garbage or IV injection periodically. After a certain period of time, we will identify how much different in the aspect of mitochondrial functions between control and test groups. We can expect some effects using selenium quantum dots in the aspect of functional improvement. As light harvesting becomes improved, higher amount of ATP could be acquired, and in accordance with that, cell viability, cellular metabolic activities, growth, and regeneration activities could be improved. It will show a decrease in the ROS production, and this can lead to delaying the senescence of the cell. But there may be some problems. No matter how much toxicity is minimized, concerns about in vivo or intracellular toxicity caused by selenium cannot be ignored. Selenium quantum dot synthesis is not yet advanced, which is expensive and complicated. To improve these problems, we have thought about two alternatives. First, toxicity reducing quantum dots should be invented, such as carbon or silicon quantum dots, or core shell structures can be applied to selenium quantum dots to protect selenium-coated surfaces. We also expect some contributions of this project on research science and human disease fields, advancement of mitochondrial research, development of new therapeutic approaches, quantum technology and medicine, interdisciplinary scientific contributions, and lastly, improving human health. As mitochondrial dysfunction-related human diseases are increasing, we need to develop new technologies and therapies to treat. This is the expected timeline if we conduct the experiments from synthesis of selenium quantum dots to in vivo and in vitro experiments. We think it'll take at least 1 year, and the expected budget is as follows. This is the end of our presentation. Thanks for listening.